Okay, so Bismillahirrahmanirrahim. Welcome to day 3, first session. We are talking about introduction to Gröbner basis and its applications. So far, we are able to have all ingredients which we need to define Gröbner basis. What we left with is Devian algorithm. We have already defined that all orderings and all those stuff. And now we are going to extend concept of Gröbner basis and concept of Devian algorithm from one variable to more than one variable. Okay, the first thing we are going to have is this notation of reduce. I mean, you want to reduce a certain polynomial using the other polynomial. It's like same by saying that when we divide two polynomials and after division we get the remainder, so you can say that remainder is actually reduced. So let's define it like this, that we have f, g and h, three polynomials such that g is non-zero. It's because we are going to use g. We say that f reduced to h mod g in one step if and only if leading monomial of g divides monomial x alpha with non-zero coefficient c alpha from f, then h is f minus this one. So let me explain this thing a little bit here. So what we actually want to say, that we have three polynomials f, g and h in k of x1 up to xn, and we are going to reduce f to h using g in one step. So this is the notation, that you reduce f to h using this g. Okay, so what is the procedure? It's similar to what we are having in the division, that for example g, the leading monomial of g, of g with respect to given ordering divides a monomial in f. Okay, so there one thing is important. Since we are, it's not the division, it's just the notation of how can we reduce a polynomial. Okay, so the condition is that leading monomial of g should divide some any monomial from f. Okay, then what we will do, we will have this h is equal to f minus c alpha and that monomial. Okay, and leading coefficient of g into leading monomial of g and times g. Okay, so let me explain this in one thing. So we one by one. So there is f. We actually multiply g with that monomial which is divisible by the leading term or leading monomial of g. Okay, and we divide it with leading coefficient of g into leading monomial of g. Now this leading monomial of g actually divides this monomial. So for sure we will not get any fraction in the form of monomials. Yes, there is this leading coefficient. So leading coefficient, leading monomial becomes leading term, and this monomial is already in f because we have chosen that monomial which is divisible by this leading monomial of g. Okay, so when we will multiply it with g, this term will be cancelled out with the leading term of g. There will be 1, and then we are only left with c alpha x alpha. Okay, and what will happen, that this term is already there, and then we have this negative sign, it will be cancelled out. So it's actually cancel out the term which is there in the in this f. Okay, so that means in the end what we will get, we will get a different shape of monomials. That's what we are saying, that this nu is equal to h, that we have reduced f using this leading monomial, leading term of g. Okay, so this is one notation, but it doesn't mean that we are going to have, the whole division. This is just first step. It is similar to saying that when we have, for example, terms like 2x1, x2 square plus some x2 square, and we want to divide it with x1 and x2, for instance, plus 1, then what we will do? We will have to multiply this term with 2 times x2. This 2 times x2 is nothing, just having this expression. So you can check that this is similar to saying that we are going to multiply that with 2x. So instead of this monomial, we will get this 2x. Okay. So this is one way of reducing one polynomial to another polynomial. Okay. So now we are extending this concept of this division. In this extending concept, we are going to have, we have seen that there are h1 and h is such that this is now you can say somehow step by step, one by one. Now we are not reducing it by one polynomial, we are reducing it step by step, and finally we get like we can use again and again g unless there is no term in f which is divisible by any of the leading monomial of g, because every time we need a term in f which is divisible by leading monomial of g. This is the main requirement of this process of reduction, that leading monomial of g should divide some term in f, and after reduction that term will be cancelled out. So this is the whole thing about this reduction. So if as soon as there exists a monomial which is divisible by leading monomial of g, then this process will continue, and we can have this step by step. Okay, first we get h1, then h2, and so on, and ultimately that is for sure that in each case we will reducing the values of this f. Okay. Now continue in this way, we can end up with, in this case when we are dividing one polynomial with the other one, we can end up with the polynomial which is actually, we can say, okay, this is the quotient in which we add up all those factors which multiply with g, and then in the end we will get some remainder. So we will extend this concept when we are having more than when we need to divide it with more than one variable. So let's do one small example here. So in this example we will having this. So in this example we have f is equal to x1 square x2 plus 4x1 x2 minus 3x2 square, and we are going to divide it using this g, and this g is equal to 2x1 plus x2 plus 1. So this is equal to g, this is our f. And again, in any type of division, what we need, we first need to define our rule of ordering, that which ordering should we use, that we need to fix in each calculation. That is important, that whenever we selected our ordering, we'll keep that ordering till the end of that calculation. So in this case, when we are having this f and g, and we are going to have this Deglex in this example, Deglex ordering. And as you remember yesterday we have defined three ordering. One was lexicographical ordering, one was graded lexicographical ordering, that this is Deglex, and then graded reverse lexicographical ordering. So you can repeat these examples just for practice by changing the ordering. We will see that after changing the ordering, all calculations will be different. Okay, because once you change the order, then there will be different leading monomial and so on. Even if in this case, if you are taking this Deglex with x1 is greater than x2, then this is the leading monomial. But if I change even this ordering among the variables which we discussed yesterday, that if I choose x2 greater than x1, then entirely thing will be changed. Okay, so for this for only coming back to this example, we have this Deglex and we have this x1 is greater than x2. Okay, so with that, this x1 is the leading term. Okay, that's fine. And now here the degree, first we'll see the degree of is 3, this is 2, this is 2, that is fine, that should be in the first position. And then between these two, since we are getting x1 is greater than x2, so this is already in the order. So this is the order we always use, that first we will write our polynomial in the descending order. This is first requirement. Okay, now coming back to the same calculations. So what we were supposed to do to get that h, you remember we say, okay, h is equal to f minus, we have this monomial, particular monomial. In this case, we will choose the leading monomial of f. Okay, and over this leading coefficient of g with leading monomial of g, with respect to that ordering and we multiply it with g. That's what we need to do. So in this case, the leading term x1 square x2 is divisible by this x1. Okay, so that means instead of this c alpha and we write it like c alpha multiplied with the ax e. Okay, so in this case this is equal to f minus, this is in this case is x1 square x2, and we need to divide with leading term of g. So leading term of g is 2x1 and we need to multiply with g. So this is f minus, this is 2x, so it is x1 x2 by 2. Okay, so this is very normal procedure which we always do to have this division, but in that normal procedure actually we were all this factor is already in our mind that we need to divide it this with this and we have to multiply it with the element of g. So in this case we divide this thing with this leading monomial and we multiply that factor with g, and this factor in this case is x1 x2 by 2, and we multiply it with this and we get this. There is no need of writing f there, so we get this x1 square x2 plus this x1 x2 square by 2 and plus x1 x2 by 2, and we get this. Since we are going to subtract it with this from f, so we'll get this. This will be cancelled out, as I told you already that there will be a there will be cancellation of that term, and then we have this x1 x2 square. Again we need to write it in the form of ordering, plus we add these two terms and we get this 7 by 2 x1 x2 minus 3 x2 square. Okay, so this is the factor, this is actually reduction we get using this g to this f. Okay, this is one step. So the next step we'll continue this process. This is about division of one polynomial with the other one. We will continue the same process. Next we will see that whether it is leading, non-leading term is this one. Is it divisible by the leading term of this g? If it is divisible, then we will repeat that process. And if it is not divisible, then we'll take it into remainder. Okay, we'll continue this process, and in the end you can check that in the end we get that the remainder, the final term, we get this 1 over 4 x2 cube minus 9 by 2 x2 square minus 7 by 4 x2, and this process will continue unless we get all remainder, in which remainder there is no term divisible by that g, that leading monomial of g. Okay. Now this is the main definition of division algorithm, and in this definition what we are given with in the division algorithm, this is important actually. In this division algorithm we need to see what we are given with and what we are going to get after applying this division algorithm. Okay, so as we discussed in the first lecture that we are going to solve this ideal membership problem. In that ideal membership problem we have an ideal and we want to see that whether that the given polynomial belong to this or not. Okay, so what we were looking for, we want to see whether this f is in this f1 f2 and so on fk for example or not, that we want to see. Okay, so what we are going to do, we are going to divide this f with this f1 f2 fk. The example we just finished, in that example we have 1f 1g, so we are in that example we are supposed to divide that f with a given polynomial, but now we have one polynomial and we want to divide that one polynomial with a set of polynomials. So that's the extension of division algorithm from one variable to more than one variable we are looking for. Okay, so that means what is the input? The input is we are given with some f and we are given with some set of polynomials fk, and this is our input of the division algorithm. And what would be the output? Output means that we need quotients. Okay, but in this case we are not dividing one polynomial with the other one, we are dividing one polynomial with a set of polynomials. That means we need a set of quotients. okay, and also we want to have a remainder. So what is the output should be? So output should be that we have like we have this uh, quotients against each polynomial, which is say we can call it as q1, q2, so on, qk, and we need our remainder. Okay, this should be our output. So in this process, in the end, we will able to find, like in the case of two polynomials, we were writing that f is equal to q times g plus r, but now in this case we will write f is equal to, since q1 f1 plus q2 f2 plus so on plus qk fk plus r. So this should be the expression we are looking for when we divide this f with set of polynomials. Okay. Now what is condition on this r? In this case, in the case when we are looking at one variable case, we're stopping the division when degree of this r is less than the degree of g. Okay, we stop at that place where degree of r is less than degree of g. There we can, okay, we cannot continue this division anymore because there is no more term in r which is divisible by this leading monomial of g. Okay, again the important part is we are looking for leading monomial of g. Okay, in this case we have not g, only one polynomial, we have set of polynomials. Okay, f1, f2, fk, and against that set we have a set of leading monomial of f1 with respect to given ordering, so on, leading monomial of fk with respect to given ordering, and we have to check for each of them. So the condition on r in this case would be that no term in r is divisible by any of the leading monomial of f1, f2 and fk. So this is extension of division algorithm from one variable case to more than one variable case. Okay, and also the difference is we are not going to divide with one polynomial the other one, we are going to divide f with a set of polynomials. Okay, so this is our first goal of today, that we will define this division algorithm. We will define a procedure to have this input and to find this output. This is our first goal. And also, since in each of these calculations there is involvement of leading monomial, okay, so that means we need a rule first. In each calculation we will fix an ordering, this one. So we need to fix that ordering. After fixing that ordering, we will be able to find all these calculations. So this is the whole thing, our first part of today's lecture. So now we are going to define that division algorithm, and then we will apply that division algorithm to a few examples. Okay. So okay. So this is the definition which I have already discussed, that in this definition we call our polynomial r to reduce mod a set of f if of these non-zero polynomials from f1 to fs. Of course, like in the case of two division polynomial of between two division, the one which we are going to divide with should not be equal to 0. In this case we are going to divide with set of polynomials, so that all set of polynomials should be non-zero. Okay, so if and only if either r is equal to 0, like in the previous case remainder can be 0, but or no monomial with non-zero coefficient in r or no term in r is divisible by any of the leading monomial of fi. So this is the same condition which we already discussed on the board, that we are looking for that remainder. If this process is complete, then we'll say that we apply this division algorithm. And we there is a notation, there is another notation. So in this case we okay, we want to divide this f with this f1 up to fk, and we call it as a set F. So after having this set F, and we get this remainder R. So what we actually have, that we use this F, we divide that F with this set of polynomials F, and we get a remainder R, and we have in the notation a plus sign there, that with after some multiple steps after multiple steps we use this capital F set of polynomials on set F to reduce it into remainder R. So this is, we can simply say that F is reduced to R using this F. So this is a notation that F is reduced to R using this set F. This plus sign means it obtained after you having this multiple steps. Okay, good. So so now we are going to have the procedure to find this remainder. This procedure is written in the form of this algorithm. Indeed, in the algorithm, we have data. We are given to give them F1 up to Fs, and F, there is a difference between the notation I use on the board and notation given on the slides. Like I was using this Fk, but here is I use Fs, and also the instead of quotients is written there U1 up to Us instead of Q1 up to Qs. So this is just a matter of labeling. So the input is again a single polynomial and set of polynomials F1 and up to Fs, and output is the quotients U1, Us, and then there is a remainder R. And what we want to have, we want to have this expression that F is equal to U1 F1 plus U2 F2 plus so on up to Us Fs and plus R. Okay, and we want to reduce this F into this R. Reduce means that no term in R should be divisible by any of the leading monomial of F1 up to Fs. That means we are properly reduce F into R. Okay, so there is a procedure step by step. You can go through from this procedure slides you already have. So in each steps, what we do, we actually use one of the polynomial to reduce F using that particular polynomial. What is the condition on that polynomial, how to select that polynomial, what to multiply, that I will explain you differently. But the idea is that in the Wien algorithm, we will apply it one by one, step by step, and in the end we will get the remainder. So that's what written in the form of this algorithm, that in each step you select one polynomial, you multiply it with that similar multiples that contain leading F divided by leading term of G, and then we multiply with G, and just to cancel out the terms. That procedure we will repeat again and again unless we get a remainder in which there is no term which is divisible by any of the leading monomials. So once a term is divisible by leading monomial of some GFI, we have to repeat that process. Okay, so let's explain this process more using one example. So here is the example. So here is the example that we have to divide F with F is x1 square x2 plus 4 x1 x2 minus 3 x2 square, and we have to divide this F with set of polynomials F1 is equal to, I think this example is containing only one polynomials. That's okay, that's fine, we can, okay. So F1 is equal to 2x1 plus x2 plus 1, and Okay. And here is only one polynomial. So we first do it for one polynomial, then we will extend it to more than one polynomial. So in this example, we are having only one polynomial. We want to divide that one polynomial with that f1. Okay. Now again we have this x1 square x2. There is we are using the ordering, lexicographical ordering. Degree lexicographical ordering with x1 is greater than x2. Okay, so we have this f1 here, which is 2x1 plus x2 plus 1, and we need to divide. Here leading term is x1, here leading term is x1 square plus x2. I think just to make it more interesting, I think I should choose a different example. So example is f1 is equal to xy minus 1, f2 is equal to y square minus 1, and f is equal to x square y plus x y square plus y square, and we are going to have lexicographical ordering with x greater than y. So let's focus on this example. In this example, we want to divide this f with f1 and f2. These are two polynomials. Okay, here one thing is important in applying this algorithm, Devian algorithm. We have an initial ordering among the polynomials. For example, we say that we are having this f1 and f2. So we fix an ordering among the polynomials. Okay, there is a reason by doing so that I will explain after completing this example. So we are going to divide f with this f1 and f2. Okay, we fix that, and then what we actually have that by applying that procedure, we have to start as follows, that we have this f and we want to divide that f with f1 and f2. So first we have to write f in descending order. So here lexicographical ordering with x greater than y, then this is the right way to write that polynomial, number one. Number two, also for the polynomials in the set of division, it's xy minus 1 and y square minus 1 is again in the order. Okay, then we need to check whether the leading monomial of f is divisible by any of the leading monomial of f1 and f2. Okay, here leading monomial of f1 is xy, leading monomial of f2 is y square. So this is divisible by leading monomial of xy, only one. For example, if I am having this square as well, for instance, if there is x square as well, then in this case f1 leading monomial of f is divisible by leading monomial of f1 and f2. In this case, since it is divisible by leading monomial of both polynomials, then and we are going to divide it with f1 f2, then that means f1 has the preference. Then we have to choose leading monomial of f1 if both are dividing the leading monomial of f. But in this case, since only f1 is dividing leading monomial, then it's fine. We'll start with f1. So f1 in this case is again same term, that this term x square y divided by leading term of f1, which is xy. So we need to multiply that f with this x. So that means we have this x times f1. Okay, so x times f1 means we have this x square y minus x, and we get this, we have to subtract it. So we get this x y square plus y square plus x. So this is, we want to write in the form of leading terms in the lexicographical ordering. So this is the right ordering, y square. So we get this xy square, x and y square. Okay. Now second, this completes our first loop, that we have completed our first step. In the second step, we will repeat the same. We have to check the leading term. The leading term of this reduced polynomial, is it divisible by any of the leading terms of f1 and f2? It is divisible by a leading term of f1, it is divisible by a leading term of f2. So this is the case we have already discussed, that in that case f1 has the preference. So first we will choose f1 leading, in this case we will choose f1 to reduce it. So this is the important step we will follow in each case, that we have a line of polynomials and we will check that which leading monomial divides the leading monomial of f, and we will choose the first one, the first which is written in the list of polynomials. So in this case again we will use f1. So again using same technique, we have to divide, we have to multiply that f1 with xy square, we divide with xy, we get y, so it's plus y times f1, and we get x y square minus y, and this I get negative plus, it will be cancel out, and then again I have to write it in the form of this x ordering, so it's x plus y square plus y. Okay, now the leading term is x, but this, now we are going to third step. Okay, the first step we get this, in the second the first step we get this, the second step we get this, and now we are going towards the third step. In the third step we have to check the leading term if it divisible by any of the leading terms of f1 and f2. In this case it is not divisible by a leading term of f1, it is not divisible by leading term of f2, so we will take that x into the remainder, so it will go to the remainder r. We are starting making the r here because it's not divisible by any of the leading term of f1 or f2. That's what the condition on remainder is, that no term in r is divisible by any of the leading term of f1 and f2. So it will go to the remainder, and what we are left with, we are left with y square. Now this we have to check that whether it is divisible by any of the leading monomial of f1 or f2. Then it is divisible by leading monomial of f2, so we will use now f2. So this times plus we have 1, so it's simply, this is y square, this is y square, just needs to multiply with 1, so with simply with f2, so it will give us y square is so it's y square minus 1, this is minus, this is plus, and I get this y plus 1. Okay, so it means that now we are left with, in the step 4, with y plus 1. Thus the leading term of this one is y, which is not divisible by any of the leading term, so it will go to remainder r, and also this one will go to the remainder r. So remainder will becomes x plus y plus 1, and when all terms goes to the remainder r, we are left with 0, and this is the point where we will stop this division. So that's what we need to do. So in this case we have in the quotient we have multiple of x, we have multiple of y, and we have this f2 multiple of 1. So we can write it in the form of doing algorithm. You remember we have to find u1 and u2. In this case this is equal to u1 f1 plus u2 f2 plus r. Here u1 is, we can get it from the multiples of f1, and here multiple of f1 is x plus y times f1 plus f1 f2 plus f2, so multiple of f2 is 1 times f2 plus we have this remainder x plus y plus 1. So here we have this division, and by same notation we can say that f is reduced to r, which is in this case x plus y plus 1 with respect to this f1, using this f1 and f2. This is the notation we were talking about. Okay, let me repeat it within 1 minute. That what we have to do, we are given with the polynomial f, we are given with a set of polynomials. In this case we have only 2 polynomials. We need to first arrange all polynomials in the given ordering. Okay, Once we arrange all polynomials in the given ordering, we will start with the leading monomial of f, and we'll want to check that which of the leading monomials of f1 or 2fs divides the leading monomial of f. And we are going to divide f with an ordered family of f1 up to fs. So that means this ordering we fix in the start among the polynomials as well. So then when we will check that whether f is leading monomial of f is divisible by any of the leading monomial of fi's, we have to choose the first polynomial whose leading monomial divides leading monomial of f. Okay, always. So and then we will use that particular polynomial to reduce f into the next polynomial, and we will continue this process, same process, and in the end we'll stop that process when we left with 0. Why? Because in each step, if there is a term which is not divisible by any of the leading term of f1, f2, we will take that term to the remainder. So it's a step-by-step procedure in which we are building the quotients and we are building the remainders, and in the end we get both quotients and a remainder. Okay, this is the procedure. So one thing which we haven't discussed, that why should we have this order? Okay, so this is important. So let's repeat this same example. Let's repeat this same example with, instead of having f1 this polynomial and f2 this polynomial, let's have it by saying that okay, this is equal to f1, this is equal to now f2, and this is equal to f1, just changing the order of this f1 and f2. Okay, so let's repeat this example by changing the order. Now we are going to, or simply you can say, now we are going to divide f with our original f2 and f1. So we change the order of f1, f2. Okay, so let's repeat the same example. Oops. Okay, let me write f1 to there. So we have this f1 equals to x y minus 1, f2 is equal to y square minus 1, and we have this f is equal to x square y plus x, y square plus y square, and now we are going to divide f with our f2 and f1. So I'm just using the same notation so that it will not get confused. So f2 and f1 means now the preference of leading term is f2, not f1. Okay, and we are having this lexicographical ordering with x greater than y. Okay, so as a first step, we have that we have to check whether this f leading term of f is divisible by any of the leading term of f1 and f2 in this case. Again, the first step is same, because only f1 divides. When only one polynomial divides, then we don't need to check anything. But if we have a plenty more than one polynomial, then we have to choose the first one in our given ordering of the polynomials. So here again we will use f1, and f1 means we have to multiply with the x f1, and we get same x square y minus x, and this will give us minus plus, it will be cancel out. Again we are writing in the order x y square plus x plus y square. Okay, now we are going, now there is a change. Now this xy square, the leading monomial of this next factor, is divisible by leading monomial of f1 and leading monomial of f2, but now the preference is not f1, now the preference is f2, because we have changed this order. Okay, so that means now we have to use this f2. So in this case we multiplied it with the, so this is xy square, this is y square, so we need to multiply with x and f2, and by doing so we have this x y square and we have this minus x, so it will give me minus plus, so it will cancel out. I get 2x plus y square. Now this step 3, this 2x is not divisible by any of the leading monomial of f1 and f2. That means this 2x will go to remainder r, and we are left with y square, and now y square is divisible by only the leading monomial of f2. So that means we have to just y square is same, so we have to add f2 there, and we get this y square minus 1, negative, it will cancel out, we are left with 1, and since 1 is not divisible by any of the leading monomial, that means this one will go to the remainder r, and we are left with only 0 there, and we stop this procedure. So that means we just recompute same example by changing the order of f1 and f2. Now let's see what we are having in the form of u1 and what we are having in the form of u2. Again, u1 means coefficient of f1, and u2 means the coefficient of f2. So in this case, we have this f to be same f1 f2. So we get this f is equal to f1. Now multiple of f1 is only x times f1 plus f2 is x plus 1, so it's x plus 1 times f2, and the remainder is now 2x plus 1. So you can see that by changing the order of the polynomials, we get entirely different quotients. Not only the quotients, but also we get different remainders as well. Okay. So before going to the break, I just want to clarify this point because it is important. That what was our initial goal? Our initial goal was we want to find whether f belongs to some polynomial set of polynomials or not in the form of ideals. And you remember when we have a system of polynomials, say f1 is equal to 0, f2 is equal to 0, so on, fs is equal to 0, then in system of this polynomials, the order of equation does not matter. I mean, if I put f1 in the second position and f2 in the first position, it will not change the solution of the system. Okay, so we can place any equation at any order, and same is true for the ideal as well. In the generating set of ideal, if I replace position of f1 with some other polynomial, then the ideal will not change. Okay, and what was our idea? Our idea was to divide this f with this thing and see if the remainder is 0. If remainder is 0, we'll say that okay, f belongs to this ideal. If remainder is not 0, f does not belong to that ideal. But the procedure we have so far, in that procedure, all things are dependent on the order of f1, f2 and set of, or if there are more than f1, f2, more than two polynomials, then we depend upon the order among those polynomials. So that is not good. That is not true, because in this case, if we change the order, we get remainder x plus y plus 1 and remainder 2x plus 1. So maybe with one combination we get remainder 0, with other combination we get remainder doesn't equal to 0. So, and also it's not true that we can decide on the basis of this procedure. Maybe we are getting 0, maybe you are getting not 0, or you are getting some different remainder. So the main goal is now to find that procedure which is independent on the order among these polynomials. Okay, I think with this point that our next goal is to rectify the procedure so that we can get only the remainder which does not dependent on the order of the polynomials. I'm just going to give you a hint that this, if we are having a Gröbner basis, our topic, then it does not depend upon the order of the polynomial. So it's all about the thing about Gröbner basis, that or simply you can say in this case this f1 and f2 is not a Gröbner basis, because changing the order we are getting this different remainders. So Gröbner basis means whatever order we have, we will get a unique remainder. So we'll start after 10 minutes. Okay, welcome back. Up to now, what we did, we defined polynomial ring, we defined ordering among the monomials, we define Debian algorithm, and we end up with the thing that with that Debian algorithm, when we define going to divide one polynomial with set of polynomials, by changing the order in that set, we are getting different remainder. So that's our main problem now, to have this unique remainder. And as I told you at the end of last lecture, last part, that Gröbner basis will solve our this problem. Okay, this is one thing. The other thing about Gröbner basis is, before we are going to define, now we are about to define this Gröbner basis, there is one more thing I need to define, and that is initial ideal. And that initial ideal is defined as that S be any subset of this polynomial ring and variable. And again, in everything we need ordering, which make us sure that on which side we need to go. So we fix a term order in that S, and we say that initial ideal, which is denoted by in of S in this case, is actually generated by all leading monomial of F, so that F belong to S. Okay, and called its initial ideal. So initial ideal means you have you can say that you have a collection, you have a collection of you have a collection of polynomials, or in the form of ideal, and you want to do you define initial ideal to be the ideal generated by leading monomials of all polynomials in that collection or in that ideal. That means if we have an ideal I in S, then its initial ideal of I is, with respect to that ordering, is defined as is generated by leading monomial of F, where with respect to that ordering, where F belongs to that ideal I. Okay, so this is the definition of initial ideal. This I of n is the initial ideal. But it is not easy to compute initial ideal. For example, if you have an ideal I, which is generated by F1, F2, and where F1 you have lexicographical ordering with x greater than y greater than z, and F1 is given by x y square minus z square, and F2 is given by x minus y z 4, for example. Okay, so in this case we have this F1 and F2 being the generators of ideal I. We have lexicographical ordering, we have x greater than y greater than z with this ordering. Then if I want to compute initial ideal of this ideal, okay, so we need to have all polynomials, the ideal generated by all polynomials belong to that ideal. And also you can see that this initial ideal is actually a monomial ideal. Okay, so that it is generated by the monomials. Okay, now coming back to this example. For example, if I just select the leading monomials of the generators only, okay, then what would be our supposition, that is it true that initial ideal in this case is generated by leading monomial of the generators only? What are the leading monomial of generators in this case? This F1 has leading monomial xy square, and it contains leading monomial x. So again we write always in the form of minimal set of generators, since x divides this xy square. So that means the initial ideal in this case is x, if our calculations are right. Okay, now if I look at these two polynomials, if I subtract f minus y square F2, then what I will get, this is just I make this factor, what I will get, that xy square minus z square, I multiply F2 with y square, so minus x y square plus I get y cube z4, it will be cancel out, and I will get y cube z4 minus z square. And this factor which I just construct here it is a multiple of f1 and f2, which are actually generators of I. That means this factor belongs to I. So we get a polynomial which is in I, but that polynomial is not a multiple of x. On the other hand, when we selected only the generators of I, we thought that maybe x is the initial ideal generated by x. So this is somehow the counter example that we cannot choose only the generators. What definition says? Definition says it is generated by all those polynomials which are in the I. It's not talking about only the generators of that ideal. Okay, so that means this initial ideal is wrong, is not correct. So we need to find some other method to find initial ideal of given ideal. Okay, so this is the second thing. Now I can say that like previously we says that order does not matter if the set of polynomials are Gröbner basis. The second definition is we can compute initial ideal only by getting leading monomial of fi's or their generators if those generators is actually a Gröbner basis. So this is the definition of Gröbner basis, that I be an ideal in polynomial ring and we have a fixed term order. We will change the order, we will change the Gröbner basis as well. So we have a fixed term order. A set of non-zero polynomials in I is a Gröbner basis with respect to that ordering if and only if f belongs to I such that f, for all f belong to I, leading monomial of gi divides leading monomial of f. This is same as what we have definition of the initial ideal, that collection of those polynomials whose leading monomial divides all the leading monomials of f which are in that ideal I. This is similar to saying that a set of polynomials will be a Gröbner basis if their leading monomial generates the initial ideal. It's against this counter example that we can, on the other hand, we can say that this f1 and f2 is not a Gröbner basis. Why? Because its leading terms does not generate the initial ideal of that ideal I. Okay, so this is the definition of the Gröbner basis, that there should be a ideal, there should be some generating set which generates whose leading monomial generates the initial ideal of that given ideal. Okay, this is one thing. Also day before yesterday we were talking about that every ideal is finitely generated, and it is generated if there is a monomial ideal, then it is generated by Dixon's lemma, and if it is generated by polynomial ideal, then it is because of Hilbert basis theorem. So since we are going to define Gröbner basis for certain ideal, so first I think we should just go through from the proof that every polynomial ideal is finitely generated. That means we are just should go through a little proof of this Hilbert basis theorem. So let's have a very simple proof that the statement is, so Hilbert basis theorem let I in S be an ideal, then I is finitely generated. So that means there is a finite set of polynomials which generates that ideal. Okay, proof. Okay, so since I is finitely generated, so there exists, we need to prove that I is finitely generated. So since I is an ideal, then that means by Dixon's lemma, so what Dixon's lemma says that every monomial ideal is finitely generated. So this ideal will have a initial ideal, and that initial ideal is finitely generated. So by Dixon's lemma, initial ideal of I with respect to fixed ordering is finitely generated. What does it mean? It means there exists a set of polynomials g1 up to gk in I such that initial ideal of I is generated by leading monomials of these polynomials with respect to fixed ordering. Initial ideal, so it means it's generated by finite many polynomials, and by Dixon's lemma, and we have like this. And now we will show that actually we need to show that actually I is generated by this g1 up to gk. So we need to show that those polynomial itself generates I. If we prove this, then that means we are done, because we need to show that I is generated by finite many polynomials. Now since these polynomials we are taking from I, so obviously their combination will always contained in I. So this, out of this equality, this inclusion is obvious. Since each gi's are from I, so their combination will also from I. So this inclusion is obvious. Now we need to show that if we take a polynomial from I, we need to show that that polynomial is a multiple of g1 up to gk. If we prove this, then we are done. Okay, so let's do that. So let's say we have some f belongs to I, and by same our division algorithm, we divide that f with that set of polynomial g1 up to gk. So after by division algorithm, we get f is equal to some u1 g1 plus so on plus uk gk plus some r remainder. Okay, so if this remainder r is 0, if r is equal to 0, that means f is a multiple of g1 and g2. We are done. Okay, but if r is not 0, then this implies from this equation we get r is equal to f minus u1 g1 minus u2 g2 minus so on minus uk and gk. Now we are taking this f from I, so this belongs to I. This g1 g2 gk are also we have taken from ideal I, so that means they're all combination, this combination will belongs to I. So there this difference will also belongs to I. So that means this r belongs to I. But if r belongs to I, that means leading monomial of r will belong to initial ideal of I. But we says that that initial ideal is generated by leading monomial of g1 up to leading monomial of gk. So since r belongs leading monomial of r belongs to this combination of leading monomials, that means sum of the leading monomial divides leading monomial of r. But on the other hand, by division algorithm, r does not contain any term which is divisible by any of the leading monomial of g1 up to gk. So that means this is a contradiction. On one side we are saying that leading monomial of r is multiple of some leading monomial of gi's, and on other side by division algorithm we are saying that r does not contain any term which is divisible by any of the leading monomial of g1 up to gk. This is a contradiction, and this is a contradiction because we are taking r non-zero. So this means r is equal to 0. R is equal to 0 means f is a multiple of g1 up to gk, and that's what we need to show, that I is actually contained in this g1 up to gk. So both inequalities we have just seen that it's true. That means I is finitely generated. So that's what we need to show, that every ideal in the polynomial ring is finitely generated. Okay, so I think that is important because we are going to define Gröbner basis for an ideal. So we need to first show that actually every ideal in the polynomial ring is finitely generated, that we can find a finite set of polynomials which generate that ideal. So we have already defined the definition of the Gröbner basis, and that definition states that set of those polynomials whose leading monomial generates the initial ideal of I. Okay, let's move ahead. We should be a little bit fast because we are running out of time and we have to complete this Gröbner basis, and then I want to give some couple of examples of the application of Gröbner basis as well by tomorrow. So let's go ahead. So we have this initial ideal, then there is a result. I have few results. I will just explain its statements and I will not going to prove it, but you have already the slides. You can go through the proof of those results from those slides. Okay, the first result is that we have this ideal, non-zero ideal, and G is up to G1 up to Gk is a set of polynomials from that ideal I, and we have fixed a term order there. Okay, then we says that following statements are equivalent. The first statement is that set G is a Gröbner basis of I with respect to ordering. So for each Gröbner basis, we have to fix an ordering. So we change the ordering, we have a different Gröbner basis. It all depends upon the leading monomials. Okay, so with respect to fixed ordering, G is a Gröbner basis. Number one, that for all f belongs to I, f is reduced to 0 with respect to this G. Then if f belongs to I, then this is actually this 2 and 3 are just similar, that we are going to have since it's reduced to 0, that means we can find some quotients so that the remainder is 0. So that's what is written there, f is equal to f h1 g1 plus so on plus hs gs, and with the leading monomial of f is maximum of this one, because if some terms are cancelled out, is still there. And then the last one is initial ideal of I is equal to initial ideal of that G. So that this is the part of definition. So these four statements are equivalent, that if one holds, if G is a Gröbner basis, that means that f will be reduced to I for any f belongs to I, f will be reduced to 0 with respect to that G. The third statement will give that if reduced to 0, that means we can find this h1 up to hj having this condition. And the fourth condition says that if this holds, that means the initial ideal of I is actually equal to initial ideal of j, and if initial ideal is same, then that means G is a Gröbner basis. So that's what I already explained, that actually this in this case we says that G is a Gröbner basis if and only if that the Gröbner basis the initial ideal of I is generated by the leading monomial of that Gröbner basis GIs. Okay, so this is the result. The proof of this result is there in the slides. You can just go through. 1 implies 2, 2 implies 3, and so on. And now there is a result that if we are having a Gröbner basis, then that set of Gröbner basis actually generates that ideal. So if G is a Gröbner basis, then that ideal is generated by that set of polynomials. The proof is very simple, that if G is a Gröbner basis, the set is already taking from ideal I, so one inclusion is okay. For the second inclusion, since it's a Gröbner basis, by previous result it will goes to 0, and remainder goes to 0 means that will also belong to that G1. So the both inclusion are same, so we can easily end up with this I is equal to G1 up to Gk. Okay, this is the result, is simple result, proof is there. The next result is says that the existence of Gröbner basis, that we always find a Gröbner basis G of given ideal. So again the proof is there, you can just go through. And now the next result says that this is just another consequence of Hilbert basis theorem. You can go through from there as well. And now we have that G is a Gröbner basis if G is a Gröbner basis of the set generated by G1 up to Gk. So this is specifying that if we are able to find a Gröbner basis, then actually it is a Gröbner basis of that ideal which is generated by that set of polynomials. Okay, now let's coming back to this our one of the, you can say, main theorem that we started with, that if we are having a Gröbner basis, then the remainder after dividing by that Gröbner basis is 0. Okay, so that was our initial scope, initial goal, to get that unique remainder. So I think I'm going to prove this result. on one direction, that if G is a Gröbner basis, then the remainder of by G is unique, and you can check the other part is also available there, but I will prove only the one part. So let's go through from that one part. So we are given with that G theorem. Let G G1 up to Gs in this polynomial K of x1 up to xn, then the following are equivalent, and it states that G is a Gröbner basis. We usually denote it by Gröbner basis by this GB, and the second statement is the remainder of division by G is unique. So it's a very simple proof. So I will go only 1 implies 2. So 1 implies 2 means we have already we are given that G is a Gröbner basis. So G is a Gröbner basis means that we have initial ideal of I in this case is generated by leading monomial of G1, so on, leading monomial of Gk, and indeed in this case our ideal is generated by this G1 up to Gk. So that's we are given with, and we need to show that remainder of division by G is unique. So let's suppose we have some polynomial f in the polynomial ring, and suppose we are given with two different remainders by dividing this G1. That is, you remember we already have gone through an example. In that example, the remainders by dividing f1 and f2 is different than the remainder by dividing f2 and f1. So changing the order, we get a different remainder. So suppose there exists two remainder. Suppose there exist two remainders R1 and R2 such that f is equal to some set of quotients u1 g1 plus so on plus us gs plus r1, and suppose same f we divide by changing the order. You remember when we change the order, not only the remainder can change, the quotients can also be changed. So let's say the new quotients are u1 prime g1 plus so on plus us prime gs plus r2. So we suppose we have these two remainders where this f g1 is given to be Gröbner basis. So after equating these two equations, what I get that R1 minus R2 is nothing but multiple of we equate this f with each other. So R1 is minus this, and it will give me u1 prime minus u1 into g1 plus so on plus us prime minus us into gs. So this R1 minus R2 is given by this after equating this thing. Now you can see on right hand side this R1 is R2 is a multiples of G1 up to GS. That means this R1 minus R2 actually belongs to I, because I is generated by G1 up to GS, and I'm using S everywhere should be okay. So is generated by G1 up to GS, and we have this R1 minus R2 is multiple is belongs to I. So that means its leading monomial of R1 minus R2 belongs to the initial ideal of I. Okay, if some polynomial belongs to an ideal, then its leading monomial should be in the initial ideal. Okay, now again the same argument. We have written this by using Devian algorithm, that f can be written as this one, f can be written as this one, and what were the conditions on R1 and R2? The remainders R1 and R2. In R1 there is no term which is divisible by any of the leading monomial of G1 up to GS. In R2 there is no term which is divisible by any of the leading term of G1 up to GS. Then that means in their difference there will be no term which will be divisible by any of the leading monomial of G1 and GS. If they itself does not contain any term, that means the difference also will not contain any term which is divisible by any of the leading monomial of G1 up to GS. But on the other side, we are saying that okay, leading term of R1 and R2 is actually belong to initial ideal, but in this case our initial ideal is generated by this leading monomial of G1 up to GS. That means leading monomial of R1 minus R2 is a multiple of G1 and G2. So these are again two contradictions, the things which contradict each other. So that means this is all why we have this contradiction, because we suppose that R1 and R2 are different non-zero polynomial. That means there does not exist any such polynomial. Does not exist any such polynomial means that R1 minus R2 is equal to 0. This implies that R1 is equal to R2. So this result only true when we says that this set G1 up to GS is actually a Gröbner basis, because we use this fact to show that such polynomial does not exist, and that means R1 and R2 is equal to 0. That means we have a unique remainder. So that's what we're supposed to prove in this result. So this is 1 implies 2 and 2 implies 1. The result is there. You can go through from that part. So there 1 implies 2. This is 2 implies 1. That if the remainder is unique, then we are having this Gröbner basis. So all proof is there. Now up to now, what we did, we started with the polynomial ring, and we defined its ordering, and then we defined this Devian algorithm, and then we say that we define this Gröbner basis, and we just explore some properties of the Gröbner basis, that it has unique remainder, it will define the initial ideal and so on. But we haven't computed the Gröbner basis yet. Okay, so now we are moving towards the step to compute a Gröbner basis, that we are given a set of polynomials and we want to compute its Gröbner basis. Again, we have already seen the result that if it is a Gröbner basis, then actually it will generate that ideal. So in simplification, you can say you are given with an ideal which is generated by set of polynomials, and we want to compute its Gröbner basis. By having that after computation, the Gröbner basis we get will generate the same ideal I. Okay, so this is our next goal, to compute that Gröbner basis. You can see that where was the problem? The problem was about leading monomials, because if the initial ideal is generated by the leading monomials of the generators, then we are done. But if there is a cancellation among the leading monomials of generators, then there some issue exists, that then that polynomial will not belong to the leading monomial of only the generators. The actual thing is when there is a cancellation of the leading monomials in the generating set of an I, there we have an issue, there we have an trouble, that in that case we will say that okay, that polynomial will not belong to initial ideal. To come up this problem, we actually want to define a new polynomial which for sure will cancel the leading terms. So that's polynomial is called S polynomial. So we will use this S polynomial to compute the Gröbner basis. So let's go to the definition of S polynomial. But before that, before going to define its definition, let's define least common multiple of two monomials. Okay, so in the case of polynomials, it is not easy to compute LCM or greatest common divisor, but in the case of monomials, it is very easy to compute leading the LCM as well as greatest common divisor GCD. So how can we define LCM? For LCM, if we have two monomials, say we have this x, first monomial so say we have two monomials u, which is x1 alpha 1 xn alpha n, and another monomial v, which is x1 beta 1 xn beta n. Then LCM of u and v is again a monomial, and that monomial is actually x1 power, in LCM we need to take maximum of alpha 1 beta 1 so on xn, maximum of alpha n beta n. So we have powers of x1 in both monomials, and we'll choose the maximum one. If we are choosing the maximum one, then we get that that new monomial is the LCM. On the other hand, if we choose the minimum one, then we'll get the greatest common divisor. Okay, so we are looking for LCM. For example, if u is equal to say x1 x3 4 and x4, and v is equal to x1 cube x2 x3 square x4, then LCM of u and v. So here we have x1 power 1, x1 power 3, so we have to choose the maximum one. So x1 cube. For x2 we have this power 1 and 0. For x3 the power is 2 and 4, so we'll choose 4, and for x4 is power 1. So this is the LCM of this u and v. So we'll use that LCM to define S polynomial of two polynomials. So since we have defined this LCM for monomials, and we are going to define S polynomial for, not for monomial, we are going to define S polynomial for two polynomials. So we'll use this concept of LCM for the leading monomials of those polynomials. Okay, so this is the definition of S polynomials. So this is already written on the slide, so just me write that one definition on the board, and then I will compute one example so that you have some idea that what it is about. So indeed, in the definition we say we will have two f and g, and again since we are going to cancel out its leading monomial, so it all depends upon the ordering we have chosen. So let's say we have f and g, and it belongs to k of x1 up to xn, and then S polynomial of f and g, indeed we fix some ordering, is m over leading term of f minus m over leading term of g, and we multiply this factor with f and multiply this factor with g. Okay, so where this m is LCM of leading monomial of f and leading monomial of g. So since in LCM we are taking the maximum powers, that means when we divide leading term of f with this maximum powers, you will always get some monomial. You will never get any fraction there, because fraction, you can get fraction in the form of for the element of field, but you will not get fraction in the form of monomials. Okay, because we are dividing it with the maximum power. Okay, let's do one example to compute this. This combination is called S polynomial, and for this S polynomial you can see that when you divide it with leading term of f, that means the leading term of f is already there, so by division you will get 1, and you multiply that one with m. Also for the g, leading term of g will cancel out with the leading term of g, you will get another one there, and you multiply with m. So m minus m will cancel out each other for the leading terms. That means in the new expression there will be no leading term of f or g, there will be new leading terms. Okay, so let's say we have f. Example, let's say you have f is equal to 2x1 x2 minus x1 and g is equal to 3x1 square minus x2, and we fix ordering to be Daglex. Then what is leading monomial of f in this case? Is x1 x2, and leading monomial of g with respect to this ordering is x1 square. And what is m in this case, which is LCM of these two monomials, and LCM of these two monomials in this case is power of x1 is 1 there, 2 there, so it will get x1 x2 power 1 there, 0 there, so we get this x2. So this is m in this case. And now what is s? So s in this case is given by, we have m to be x1 square x2 over, we divided with leading term of g, leading term including the coefficient. So we get this 2x1 x2, we multiply it with f, which is 2x1 x2 minus x1, and multiply minus, you have same x1 square x2, and divide leading term of g, which is 3x1 square, and you multiply it with g, which is 3x1 square minus x2. So what I will get? So I will get, this will becomes 1, and I have x1 square x2, same will be there. So I will get terms like it will give me x1 square x2 minus I have this x1 1 over 2 x1 square minus I have same this x1 square x2 minus, will multiply, will get plus, and with that I have x2, so it will get 1 over 3 x2 square. So while we computing this s polynomial, two terms must be cancelled out. Like in this case, this x1 square and x2 square will be cancelled out with that thing, and what I will be left with these two factors, and these two factors will give me the s polynomial of f and g. Okay, so again the idea is to cut off the leading monomial so that we can use it to compute our Gröbner basis. Okay, let's moving ahead. This is the main criteria to find the Gröbner basis of a given set of polynomials. We will use this criteria to compute the Gröbner basis. And what does this criteria says? That we are given with g1 up to gs be set of polynomials, then g is a Gröbner basis if and only if s polynomials gi of gj for I less than j greater than equal to 1 less than equal to s. That means we are taking all possible pairs of g1 gi's. Like we have a set g which contains g1 up to gs, and we are taking all possible pairs of this set. We compute their s polynomial, that means we cut off their leading monomials by using that formula, and when we have their s polynomial, we divide that s polynomial with respect to given set this g. So division you already know, division algorithm, and then if all that factors s polynomial reduced to 0 with respect to this g, then we will say that that set g is a Gröbner basis. So this is the criteria on the Gröbner basis, and we can use this criteria to compute the Gröbner basis. How? If for example you are given with two sets g1 and g2, and you want to check that whether it is a Gröbner basis or not, what you will do? You will compute it as polynomial, and you will divide that as polynomial with g1 and g2. If the remainder is 0, you can say okay, this g1 and g2 is a Gröbner basis. If remainder is non-zero, that means you will relabel that remainder to be g3. So now you're having g1, g2 and g3, and then you will repeat that process, and this process will continue unless you get a set of polynomials which will give you Gröbner basis. Now how we can say that this procedure must stop at somewhere? We have a result that this polynomial ring is a Noetherian ring, that every ascending chain of ideals stops somewhere. So since in each step we are adding some polynomials there, or maybe we add, or we just keep checking, so ultimately this process will stop at somewhere because we are in the case of Noetherian. So this criteria will help us to compute the Gröbner basis. So for tomorrow we'll start by computing its Gröbner basis. We will be given some set and we will compute Gröbner basis using this Buchberger criteria. Okay, so these slides you are having already having the proof of this Buchberger criteria, but we'll see that tomorrow we have to compute this Gröbner basis. We have to define this reduce and minimal Gröbner basis, and also we are supposed to do at least 1 or 2 examples where we have applied this Gröbner basis, and not the least, that we also have to have the solution of that ideal membership problem which we already posted yesterday. Okay, so with these words, I'm signing off, and tomorrow we'll see, and on the last day of our lectures, where we will have compute this Gröbner basis and we will discuss some applications. Thank you.